I run Zvonko Kaiser from NVIDIA. I work on confidential computing at NVIDIA, right? And I'm driving Kata containers and confidential containers. In the next 20 minutes, I want to talk about a subject that most of confidential compute does not touch, which is the shared substrate we are running on. The silicon substrate and the Kubernetes substrate, where we are running our confidential stacks, our CVMs, or our containers. But before that, just a small recap, right? We all know containers are not a isolation boundary, not a security boundary. We started looking at containers, how to run them in a confidential environment, then extended to the full node, right, to full stack attestation, because we need to make sure that the node is as well tested, sanitized, verified. Last year, talked here as well, and made a point that Kubernetes is our lingua franca for any AI ML pipelines that we are running outside, right? So we have the container, the full stack attestation from service to silicon. We have Kubernetes, and then also running those containers to scale. And one critical part is really that AI ML on private data is really hard, right? So that's why we're all here. Why we're all doing this here. Right. So hardware attestation is necessary, right? Whether it's sufficient depends on something attestation cannot measure, which is how the infrastructure underneath is shared, right? Each tenant gets a cryptographic overlay, which is the CVM, right? You get a cryptographic overlay of your hardware, where your container or CVM is running, right? But what all the attestation and confidential compute does not cover, as I mentioned before, are the two substrates that are sitting beneath them and we are running on, which is the silicon and Kubernetes. And none of the shared substrate that they're running on is covered by attestation. Kurt Gödel is a German mathematician who proved that no formal system can verify itself from within, right? You always need an external verifier. And that's how CC works, right? We always have the external verifier. If we are having something out of band to prove our runtime is valid. The other point is runtime integrity is also not different. Runtime cannot prove its own integrity using its own facilities. So we always need something external. And that's where confidential computing heads out to the verifier, to the remote attestation. Right. So we always need something external to verify the runtime that we are running on. So if we have, for example, two tenants running on the very same stack, we have the workload overlay, the compute overlay, which is the CC. You may want to have compute network overlays as well to protect your network. You want to have storage overlays as well, right? Which is another protected layer on CC up top. On top, you have the CVM boundary and you have the attestation root of trust. And each tenant runs its own cryptographic overlays. But what we are not checking for in our use case is the shared substrate, right? If you're running on Kubernetes, we are sharing, for example, etcd, the scheduler, and the API server with every other tenant that's running on the cluster. The silicon substrate, right? All the microarchitectural features that we have, like the silicon, the cache, the bus, the interconnect, and even electromagnetic environment is shared with tenants. There's a recent attack, for example, with an antenna in your backpack listening to electromagnetic waves of a CC environment and extracting information out of those systems. If we are taking a deeper look on what we are sharing with tenants on the same node or on the same clusters, right? We have the Kubernetes control plane, we have the hypervisor, we have a physical bus, we have voltage and frequency, we have the microarchitecture state, we have speculative execution, the cache, the page cache, right? Those numbers represent attacks against each of those layers. Recently, starting from 23, right? The only thing, well, I'm not saying the only thing, but there are no published attacks on out-of-band selecting, right? Like the service processor or the Google Python or anything else. Everything that's shared on the cluster, and which is a necessity if you're running multiple tenants on the same node, are prone to attacks. I have an overview slide with all the attacks that can happen on each of those layers. I will choose one or two of them just as an example to showcase what can happen. And one critical thing is the cache, right? It sits below everything, below your CVM, below your networking, below every encryption that you're running, right? For example, an example attack TDX Ray, it did not break the confidential state. It did not break the encryption, right? What it does is just look at metadata of where specific data is stored at which specific addresses, right? So it was able to read an LLM prompt from one VM to the other. That's, if you have co-tenants on the node, you are prone to such an attack, right? And no boundary about the cache can hide what the cache sees. Every VM, CVM that's scheduled on your host is prone to a cache attack, right? Another example would be the physical bus. Just showing here some of those attacks that happened on the physical bus that broke SMP, broke TDX, because with co-tenancy, having two tenants, one of the tenant can attack the other CVM. I'm not going to the details, all of those. You can look it up and after presentation there, right? Again, none of those broke the crypto, right? None of those broke any cryptography that we made for the CVM. They share all the bus, and that's why it was possible. Another example is the hypervisor. We cannot remove the hypervisor. The hypervisor is the thing that establishes our CVM, right? So we need to live with that. And another prime example attacking the hypervisor, if you have co-tenants, is bad-IML, which essentially injected ACPI tables into the guest, and the guest executed those overwriting init system or any other binary inside of the CVM. Again, crypto was not broken. It's just the fact that we have the hypervisor, or the fact that you may have co-tenants or someone else lurking on your very same node with your confidential data. Right, and there are some other examples here for the hypervisor attacks like Heckler, VC, Sigi, Sievert, RPM, Ocalypse, all targeting the hypervisor and attacking the hypervisor and the CVM. This is a summarization of the recent attacks since 23. There are around 37 attacks against VMs, CVMs, SMP, TDX, and all those boxes are the shared substrate, the silicon shared substrate that we have for the CVMs. And if you have co-tenancy, those are all entry doors for attacking the CVM if you're sharing your substrate or sharing your silicon with a co-tenant. And again, out-of-band silicon, like a DPU or the security processor, which are not shared with the workload that has no access to those chips. There are no published CVs on that one, but we don't know if they are CVs that those companies fixed. Right, and we cannot go deeper into the stack, right? The cache is the last thing. We cannot go deeper than the CPU. There's no way, so we need to go sideways. And the one thing is, stop sharing your node with other co-tenants. The silicon was the first substrate. The second substrate is Kubernetes, right? The control plane. Kubernetes was never meant as a multi-tenant system. It was meant for a cooperative system to run pods that are trusting each other, right? The problem with Kubernetes is if you have multiple tenants on them, you're sharing etcd, you're sharing the scheduler, you're sharing the API, you're essentially sharing the complete control plane with other co-tenants. And for example, also etcd does not have any row level isolation. So the other point of this one is do not share your control plane. Have one tenant per control plane and per node. Do not share the control plane with 4 tenants. Right, and attack. The problem also is with the shared cluster is even if you, as before we said, run one tenant per node, right, to not share the silicon. But if you have a shared cluster, now you have a malicious scheduler which could use multiple tenants, schedule them on the very same node, and, for example, get a pod, a victim pod and an attacker pod on the same system, use the shared silicon substrate with the attacks that I shared before, and now you have, again, a compromised CVM or compromised workload. Several isolation architectures, right? We talked about the physically separate silicon, out-of-band silicon, right, which is one form of isolation. Then we have confidential compute with the shared silicon and hardware and software isolation. Again, if you're sharing the silicon, you're prone to attacks. And then we have also things like Nitro, where the operator is inside of the trust boundary. Again, no publicly available attacks on Nitro, but we don't know about that, right? So those are the 2 main free isolation architectures. And we are concentrating on the middle one. Again, 39 published attacks and 20 for free on those aspects. I want to make sure that this does not happen. So if you're looking, for example, running confidential containers or confidential compute, what does it protect, right? It protects your memory, which is, again, a overlay for compute, right? You need to make sure that your control plane is also isolated, right? Networking as well. Networking reaches through the host stack. You need to make sure that it's encrypted, right? Creating overlays for the network as well. Storage, the same. You need namespaces or front-end and back-ends that are separated for each tenant. There's a recent attack, Frost, which can, through NVMe SSD timings on the NVMe drive, it could deduce information from specific workloads. Also identity, like SPIFFE Inspire, right? You need to take care of this as well. And also telemetry, which is also metadata that you need to make sure that it's not shared between tenants. Right, one prime example where we just talked about is TDX-Ray. Again, the CVM or confidential compute did everything right, but the prompt still leaked. A tenant was able to read a LLM prompt, even if our encryption on the CVM, on the networking, on the storage all work. It was the shared substrate below that was shared between the tenants, which make this attack possible. So if we are talking about confidential compute, I think there's no middle ground of sharing any silicon, because as we've seen on the shared silicon, there is a constant stream of attack on CVMs, on workloads, on QEMU, on all workloads that are running there. So one point is do not share silicon. Every tenant should have his own dedicated silicon, 1 tenant per node. And as well, per tenant control planes and all the other points that I just made before. All right, to sum it up, 1 tenant, 1 node, 1 control plane, because if you start sharing, you're vulnerable. This is more of the point of view from confidential compute, right? Depending on your threat model, depending on your threat assessment, depending on your threat that you want to accept, it may be different. but from the CC point of view, this is the best way to go. And right, you need to ask yourself during the threat assessment, who are you sharing with whom, and are those parties trusted? You don't want to run trusted and untrusted workloads on the very same cluster, on the very same node. And then what do you actually verify, right? Full stack attestation from silicon to service, making sure that every part of your stack is attested. And then again, the last question would be, is your gap patchable or structurable? Patchable, can you fix a CVE, or do you need to think about your structure, about your topology, and think about to move the tenant to dedicated nodes? Because all those the other attacks that are coming there may be patchable, but also microarchitectural, but side channels as well are not most in the time not patchable immediately. Right, Miko said some time ago, if it's smart, it's vulnerable. I'm saying if it's shared, it's vulnerable. And the topology is the security policy. Thank you. Any questions? Oh. It will not solve it, as I said, and showed here, right? It just does the compute. And how you manage your tenants on your cluster is up to you, right? How you share your node, how you share your control plane, right? Often what comes up is efficiency, asking because if I have a cluster of GPUs, I want to use it efficiently. Yes, you can use it in your trust domain, but don't mix trusted and untrusted domains. You don't want to increase the efficiency in an untrusted environment with an untrusted environment. So it's up to you how you schedule what your threat assessment and what your threat model is, who you let on the node, and who has access to the node. Right? Going once, twice. Thanks, everyone.